I'm going to recap the sampling simulation that we did in class. We started out by taking a class vote. Do you prefer Batman or Iron Man? After giving people time to think about their various reasons they may support one or the other, everyone had to pick exactly one of the two. And in a class of 24 at the time, we found that 15 out of 24, or 62.5% of the class, voted for Batman. So in this particular class, we're going to define our population, or in the situation, we'll define our population as the entire class. And so we know this parameter, this proportion of the population, is 62.5%. But now we're going to play around and take smaller samples. So instead of asking all 24 of us, we're going to ask only 5 at a time and see what kind of interesting data we might get. So every student set their calculator to randomly generate a number that corresponded to each student so they could select a sample of 5 people. So we go to the math key, to PRB, and the fifth one down is randint. And since there's 24 people in this class, we did 1, 24, and we generate 5 random numbers. We continue to hit enter until we have 5 people randomly selected for our sample, 5 unique people. And those 5 people, these 5 numbers, each correspond to a person. Everyone had to write their name down on the board next to a number. And so each of these numbers identifies a unique person. And so let me just sketch out a quick little diagram. Imagine you have all the people in the class, and I won't draw 24 X's here, but let's say we have all the people in the class, and you randomly selected 5 of them that you wanted to ask, who did you vote for? Did you vote for Batman or did you vote for Iron Man? So you randomly select, let's say 5, using your calculator to help you out, and you ask those 5 people. And of the 5 people you randomly selected, let's imagine that 2 out of 5 said they prefer Batman. And then the other 3 would obviously be Iron Man, the only other choice. So we're going to look at everything from the Batman perspective for now, and we'll look at maybe why that is in some of the later videos. But 2 out of 5 in this person's sample said Batman. I'm just going to color code this because I want to show another sample here. Another person generated 5 random people to be in their sample, some of which might be some of the same people, some of which may be different people. And in this new person's sample, they found that it was actually 3 out of 5. 3 out of 5 people that they talked to said they prefer Batman over Iron Man. And we repeated this with every person in the class. Every single person in the class had to ask 5 people which one they preferred. And they each got their own little fraction. 1 out of 5, 4 out of 5, whatever it might be. First thing that we did with all that data is we made a long-run probability graph of who likes Batman. And the way a long-run probability graph works is you take a single data point in at a time and plot it on the graph. But when you add the second one, you don't just plot that one, you actually take the average of the first 2. And when you plot the 5th one, you take the average of the first 5 and plot that as the point. So I'll kind of show you what that would be like. We asked the first person what they got. And the very first person said, oh, I got 3 out of 5 that said Batman. We're like, okay, 60%. So we marked that on our graph. Second person said, oh, I got 4 out of 5. I got 80%. So we took those 2 numbers and we averaged them together, and our second point that we plot on the graph is right here at 70%. So after 2 trials, we're at 70%. Then our third person also said, oh, I got 4 out of 5 also. So again, we averaged in 80% plus 80% plus 70%, and we got something a little bit closer to 80 here. And we continue to repeat this. The next person went down. I think they had 3 out of 5. And so forth and so forth. And you continue doing this. And over time, by the time you get through the whole class, you start to get something that kind of converges on what you expect it to. Because of randomness, it might not be exactly on there, but it's going to get very, very close in the long run. The more data points you have, the less likely it is to be kind of crazy and chaotic, and the more likely it is to be exactly what you would expect from the whole population. This population number right here, 62.5%, that's where our experimental values are going to end up in the long run. So that was the first thing we did. And this phenomenon that we're seeing here is called the law of large numbers. Basically, as the number of trials or attempts goes up, the experimental probability, the data that we collect, the real data, approaches the theoretical probability, what we expect. So the real data is very chaotic at first, but as you do more and more trials, it kind of smooths out on what we expect it to be. So that's the law of large numbers. Another way of saying that with a simpler example is if you flip a coin many, many, many times, the more times you flip it, the closer your probability of getting heads is going to get to a consistent 50%. Otherwise, it might be very chaotic. If you flip a coin only 4 times, there's a pretty reasonable chance that you'll get 75% heads or 0% heads or anything like that. So more trials means your data ends up more like you expect it to. After we did this graph here and talked about law of large numbers, we did another perspective on the data. We created a histogram, or a bar graph actually. And so on this bar graph, we titled it How Many Prefer Batman to Iron Man in the stats class by taking samples of 5. So we had the number of people that could be in your sample that voted for Batman. At the lowest could be 0. You could have all people that prefer Iron Man. Or at the highest could be 5 out of 5. Since you only talked to 5 people, you can't get 6 people that said they preferred Batman. You can only max out at 5. You can't have less than 0. So these are your only options here. When we actually did this in class, nobody got 0 people who voted for Batman. We had one person who had 4 out of 5 Iron Man, 1 out of 5 Batman. So we graphed the frequency of one person who got 1 out of 5. Same thing with 2. We had one person that had 2 out of 5 Batman votes. And then 3 was quite popular. 12 people in a class of 24 found that somebody voted for Batman 3 out of 5 times when they took their sample. So half the class got 3 out of 5. So that was a very overwhelming result. And then 4 out of 5 was also pretty strong, somewhere around 8. And then about 1 or 2 here for 5 out of 5 Batman votes. So again, what this graph is basically showing is most people, when they did this little experiment, or at least a little over half the class, got 3 out of 5 people to vote for Batman from their totally random sample. Remember, we just randomly picked 5 people and asked them, and most people said 3. And that's actually a pretty reasonable guess, because we said that 62.5% of the population voted Batman. Well, if we're only asking 5 people, 62% is somewhere just a little bit bigger than 3. When you're talking about 5, 62.5% of 5 is going to be a little bit bigger than 3. So we would expect that most data is going to be close to 3. And since it's a little bigger than 3, it also makes sense that we get a lot of 4s. We get a lot of times where it was going to be 4 out of 5 people said Batman. So that was that first experiment. And what we were just trying to do is get comfortable with this idea of taking samples, random samples, from a population and trying to see what kind of results we get back with our proportions.